So in the electric drives, what we have to do, we have to control performance of a AC machine, either AC or DC machine, with various types of power electronics device. Power electronics, basically not device, we can say that in better way, power electronics circuit, just like a chopper, inverter, cycloconverter, AC voltage controller, etc. So now today we have to discuss various types of device which can help us to control the parameter of AC and DC drives. Okay, so let's start. Okay, now I have to draw some kind of block diagram, and you have to say which type of power electronics device we can use as a power modulator. Now we all know that from the basic diagram of electric drives, there should be a power modulator which can control the parameter of external device, that is external, that is the external machine which is connected with that particular power modulator. And obviously we have to connect one load, which is the rating of the load should be as per the machine rating. That means our machine can easily bear or easily hold that load without any problem. Okay, so now today I have to draw some kind of block diagram, and you have to say which kind of power modulator we can use here. Okay, I'm drawing it one by one. You have to draw it, that block diagram, in your own copy so that you can understand in better way. Okay, so let's start. Source, then this one is a power modulator. And the power modulator output is directly connected with the machine. Now, our requirement in this case, we want fixed voltage AC. Okay, and in the input side as a load, we have fixed voltage single AC. Okay, and sorry, in the output terminal we want fixed voltage DC. So So as I am, sorry, I was disconnected. So again, I am drawing. You have to say. So this one is the source. Okay. This one is the power modulator. This block represent the power modulator. And this is the output voltage. Okay. That means the output of the power modulator should be directly go to the machine, the motor which we are connected in the power modulator. So in the output terminal, we want fixed DC, fixed voltage DC in the output terminal. But in the input terminal, we have fixed voltage, single phase or three phase AC. Now, anyone tell me which kind of power electronics device or which kind of electronics device we can use as a power modulator? Anyone? Hira, Sumit, Arpan, anyone? Apply your basic knowledge and tell me which kind of circuit we can use as a power modulator in this case. Poonam, tell me. Unmute yourself and tell me which kind of device we can use as a power modulator that can change the source voltage as per our requirement, as per load requirement, as per machine requirement. Which kind of power modulator we can use? No. Sumit, IGBT is a device, but power modulator is a circuit. Okay. We know the rectifier operation. Rectifier can change or rectify the signals, fixed voltage AC to variable voltage DC. That is the function of a control rectifier. But here, in case of this, in this case, if we use as an uncontrolled rectifier as a power modulator, we can achieve our, or we can fulfill our requirement. That means our input side, we know we have fixed voltage single or three phase AC. But in the output side, as per the machine, we want fixed voltage DC. So we can use uncontrolled rectifier as a power modulator device. Now, do you understand? Hira, Arpan, yes, okay. So here the power modulator we can use, that is uncontrolled rectifier. Please write down uncontrolled rectifier or diode rectifier. Diode rectifier. Okay. So diode rectifier is used here as a power modulator device. Okay. Okay. So this is one example, or this is one block diagram. Yes, ma'am. Okay. So 1 minute. So as a power modulator device, we can use as a diode rectifier. Next, I'm again drawing another block diagram. You have to draw this kind of these block diagrams in your copy also to understand properly. Okay. Okay. Now, in the output terminal, the load, the machine which we are connected, that required variable voltage, variable voltage DC, but in the input side we have fixed voltage single phase or three phase AC. Okay, so here in this case, which kind of circuit we can use as a power modulator? I am telling you, that is control rectifier, because you can see that in the output terminal, as per our motor rating, as per our motor requirement, we want variable voltage DC, but in the input side we have fixed voltage single phase or three phase AC. So we know that AC to DC can convert easily by a rectifier circuit, but here the output voltage is variable, so we can use fully controlled rectifier as a power modulator device. So here we can write the power modulator device should be fully controlled rectifier. Okay, so this is our power modulator device. In this case, we can use a fully controlled rectifier as a power modulator device. Now, similarly, here similarly, if I draw fixed voltage single phase or three phase AC in the input terminal and the output terminal variable voltage DC, so we can use here as per our load operation, as per the motor rating, as per the load operation, we can use here half control rectifier also. That is up to our range of the motor. That means the motor should operate in which range, that we have to calculate, and that you have to know first. Then we can choose either fully control rectifier is required or half control rectifier is required. Okay, now again, this one is a source. Instead of one power modulator, we can use 2 to 3 power modulator also. Okay. So it is another power modulator. Then the output is fed to the machine. Now here in the source side, we have fixed voltage AC, either single phase or three phase. Okay. Now here variable voltage AC. We are getting from a fixed voltage AC to variable voltage AC. But in the output terminal, we are getting variable voltage DC. And this variable voltage DC is directly fed to the DC motor. Okay, so you can see that here 2 power modulator is required. One is fixed voltage AC in the supply voltage we have, Next, the power modulator which we have to use, the output of that particular power modulator should be variable voltage AC. So here we can use first power modulator. The output of the first power modulator is variable voltage AC, and that variable voltage AC is fed to the second power modulator, where we can get from the variable voltage DC, and that is fed to the DC motor. So the first power modulator which we can use, that is a transformer, okay, single or three-phase transformer. We can easily use this transformer, can change the voltage, fixed voltage AC to variable voltage AC. Now this variable voltage AC again changed by variable voltage DC. So here the second power modulator should be fully controlled rectifier. Okay. So this is our fully controlled rectifier. We can use the as a second power modulator. So this is the third block diagram. We can see that here instead of one power modulator, we are using two separate power modulator, which can help us to transform the voltage from one source to another source, and that is directly fed to the DC motor. And again, I am telling you that this kind of orientation is required for the industrial purpose, for the major application, for the pressing department. Suppose in a paper mill, okay, or in a, where the newspaper is published. So the newspaper is published by the machine. They are printed the newspaper in a particular way. So in that particular industrial application, we need this kind of orientation. Okay. Next is one power modulator. Again, this is fed to the second power modulator, and the output of the second power modulator is directly go to the motor, either AC motor or DC motor, whatever the motor is. So in the source side, we have fixed voltage AC, single phase or three phase. Okay, fine. Here that is fixed voltage DC, fixed voltage DC we require. That is our requirement. That means the output of the first power modulator should be fixed voltage DC. Now again, this fixed voltage DC is fed to the power modulator, second power modulator, and the output of that second power modulator should be variable voltage DC or variable DC voltage. Okay, so that means the first output of the first power modulator, that is fixed voltage AC, but the output of the second power modulator is variable voltage DC, fixed DC to variable DC. So now we know that here we can change first we have to use one power modulator which can change fixed voltage AC to fixed voltage DC. That is nothing but we can use here the diode rectifier as a first power modulator, right? But in case of the second power modulator, where the input voltage is fixed voltage is AC DC, but the output is variable voltage DC, so which kind of power modulator we can use here? Anyone tell me? Sumit, Sanjay, Poonam, Hira, Arpan, anyone? फिक्स डीसी से वेरिएबल डीसी में कन्वर्ट कर सकता है ऐसा कोई पावर इलेक्ट्रॉनिक सर्किट का नाम बोलो. एनीवन? सुमित, हीरा, अर्पण, पूनम, chopper, Sumit, right? So we can use the second power modulator. We can use chopper as a second power modulator. So chopper, very good. So this is the orientation of the power modulator. Okay. Similarly, if our input side we have fixed voltage, single or three-phase AC, but we want variable voltage AC, so we can use here either cycloconverter or AC voltage controller. So cycloconverter can help us to change the frequency, whereas AC voltage controller can change the magnitude of the AC voltage. Okay. So as per the machine, again I'm telling you, as per the motor, we have to choose which kind of power modulator we can use. So if you are following GK Dubey, you can see that there are various types of block diagram is there, and it is you can easily understand this thing. That is properly given in this GK Dubey book, and I am already told you that you can search in Google. So get the PDF version of this GK Dubey, and GK Dubey book is as per your syllabus. It is already there. Okay. Now, please write down each and every block diagram so that you can understand the power modulator device properly. Okay, so I'm erasing it, and next topic is fundamental torque equation of electric drives. That is dynamic of electric drives. Write down fundamental torque equation of electric drives. Fundamental torque equation of electric drives. Okay, so as per the basic model or basic diagram of electric drives, we know that there should be a source, then a power modulator, then our motor, and motor should be connected with proper load. And of course, so we want to control the motor in a closed loop way. So we have to sense the output parameters of the motor through a control unit, and then some sensing unit. That sensor unit should be passed the signal after sensing the output parameters value to a control panel, and then that control panel, that is we can use microcontroller as a control panel, we can use PLC controller, we can use PI controller, whatever the controller is. That controller unit is generated a proper signal which can fed to the power modulator again, so that we can control our motor in a closed loop way. Okay, so that is the basic schematic diagram of electric drives we already discussed in our class. Now today, whenever we are talking about fundamental torque equation, so obviously we know that the motor which we have to choose as per our operation, or as per the industrial purpose, either we can choose a DC motor or we can choose AC motor. Okay, in case of AC motor, we can choose induction motor or synchronous motor. We know that thing. So first of all, we have to study the basic torque equation. Whenever we are talking about the basic torque equation, so this torque equation, torque means obviously motor torque. There are two types of torque. Basically, we get two types of torque in case of electric drives while we are considering while we are discussing about electric drives. So first of all is the motor torque, that is we can get from a particular motor which we are connected. And then the load torque. Load torque is the load which is connected directly to the motor, or which is directly coupled with that motor. A torque is generated in that particular load, and that torque is defined as the load torque. So the synchronization of motor and the load is very much important. We have to choose the load as per our motor rating, so so that our motor can easily bear or handle that particular load and can do the proper work or the proper purpose. We can use the load. So obviously the rating should be synchronized with each other. Now I'm drawing a block diagram or the basic diagram of the motor and the load. You also draw it, because otherwise it is not possible to understand it properly. And this basic equation, basic torque equation, is very much important to understand. Okay, so the first one is motor and the second one is load. So the motor is connected with the load. Now I'm writing here motor, and this one is our load. Okay, now one thing you have to understand, that is as per Newton's third law. Okay, first of all, I want to tell you that the torque which is generated by the motor, that is represented by capital T, that is motor torque. And the load, the torque which is generated by the load, that is defined by TL. Okay, so TL means obviously load torque. So now as per Newton's third law, obviously we know that motor torque and load torque should be opposite with each other, right? Every action there should be an opposite and equal reaction, we know, and that's why we can say that as per Newton's third law, the direction of the motor torque and the direction of the load torque should be opposite with each other. Otherwise, motor can't bear the load properly. Okay, so that means if the motor torque is operating in anti-clockwise direction, so obviously the direction of the load torque should be clockwise. They are opposite with each other. Now the machine is rotating. Now let the machine is rotating in anti-clockwise direction. Okay. So this is the direction of speed. This is the direction of the speed, that is in anti-clockwise direction the machine is rotating, and the rotation speed is omega m. It is defined by omega m. Sorry, omega m. Okay, so at omega m, this entire setup is the motor is rotating at omega m in anti-clockwise direction. So obviously the load torque, the direction of the load torque should be in this way. Sorry, yes, sorry. The direction of the motor torque should be anti-clockwise, but the direction of the load torque, that is opposite with the motor torque. So it will work in opposite direction. Okay. So that is the direction of the load torque and the motor torque. The machine is rotating in omega m speed in anti-clockwise direction, and the torque which is generated by the motor, that is also operating in anti-clockwise direction in the same direction of the speed, but the load torque that is generated by the load, the direction of the load torque is directly opposite to the motor torque. Now, say the polar moment of inertia of this entire setup is capital J. That is equals to our polar moment of the setup. Okay, so polar moment of inertia of this entire setup, and that the unit of the polar moment of inertia is kg per meter square, and the polar moment of inertia of this entire setup is capital J. Now omega m is the angular speed, angular velocity, and motor torque is represented by capital T, and the load torque should be TL. So we can write the rate of change of the rate of change of polar moment of inertia, that is capital T minus TL, that should be is equals to J d of ddt that is not dot product. I'm just representing J into d dt of J of omega m. Okay, so that is the rate of change of polar moment of inertia of the system, that is T minus TL, that is motor torque minus load torque, that should be is equals to J into d dt of J into omega m. Or we can write here capital J d of omega m divided by dt minus, sorry, not minus, then plus omega m into dj divided by dt. Now, as J is the polar moment of inertia, so for a particular system, J has a particular value. So dj dt should be is equals to 0. So this value is constant, and we know that the value of J is constant for a particular system, and we can say that dj dt, the particular this value should be is equals to 0. It is a constant value. So we can write here capital T minus TL, that should be is equals to J of d of omega m divided by dt. Now that means motor torque minus load torque equals to J of d omega m by dt. Now d omega by dt is nothing but it's called dynamic torque of the system. Dynamic torque of the system. System. Dynamic torque of the system. So we can write motor torque should be is equals to load torque plus J d of omega m divided by dt. That is motor torque should be is equals to load torque plus dynamic torque. So this is the basic expression of our electric drives. That is the fundamental load torque equation, and you have to remember this thing, that motor torque should be is equals to load torque plus dynamic torque. Okay, so this one is very much important, and you have to remember this equation, that is motor torque should be is equals to load torque plus dynamic torque. Now what is the purpose of dynamic torque? During transient operation, now what is transient operation? Suppose the machine, whenever we are starting a motor, during the starting time, and whenever we are stopping the motor, or whenever we are braking the machine. Brake means obviously we are decreasing the speed, and braking means the braking, the definition of braking is to stop the machine. The process to stop the machine is of a running machine is called braking. Okay, so whenever during the starting time, during the braking time, there is a transient occur to the system. Transient means obviously acceleration or retardation. Okay, during starting time, machine will accelerate. That means acceleration will occur. We are increasing the speed. Gradually, the machine will reach the speed. The motor and that particular speed should be transferred to the load also. So that is a transient moment. So during transient time, during the starting time and during the braking time, to stable the system, dynamic torque helps the motor torque. Okay. Otherwise, during the steady state moment, the value of the dynamic torque is near equals to 0 or equals to 0. So we can say that during the steady state timing, when the machine is running during the steady state operation, or whenever we are doing the machine is doing the steady state operation, that time the motor torque should be equals to our load torque. Okay, so obviously you have to remember one thing, during steady state operation, motor torque should be is equals to load torque. That means T should be is equals to TL. But whenever the transient operation occurred to the system, that means during the starting time and during the braking time, either motor torque is increasing, motor torque is greater than load torque, or motor torque is less than load torque. So that means as per that time, during transient moment, that means starting time or braking time, that dynamic torque will help the machine to support or to overcome that unstable condition. Okay, so that is the basic torque equation of the electric drives. Remember one thing, that motor torque during steady state operation, motor torque and load torque both are equal with each other, but during the transient operation, the expression should be motor torque equals to load torque plus the dynamic torque, and that dynamic torque supports the system, support the motor to overcome the transient operation. Okay, so that is the basic expression of torque. Or we can say that, or we can write in a proper way, or we can write that motor torque should be is equals to load torque plus dynamic torque. Okay, in this way also we can write. So do you understand this fundamental torque expression? Everyone, I am telling you. I'm asking. Arpan, Hira, Poonam, Sanjay, Sumit.
Sir.
Everyone?
Yes, ma'am.
Okay. If you are having any doubt, then without any hesitation, tell me. Yes, Sanjay, Sumit. Yes, ma'am. Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay. So please write down, draw the draw the schematic diagram, as well as write down the expression. It is important. Please write down the equation. Then I will start a new topic, that is the 4-quadrant operation. Done, ma'am. Okay, Hira. Thank you. Okay. So then I am clearing all. Okay. Now, next is another important topic, that is 4-quadrant operation of electric drives. Now we know that as per Newton's third law, the direction of motor torque and the load torque are opposite with each other. Fine. Now, the 4-quadrant operation is very, very much important. You have to understand it in a proper way. Okay. If you are having any kind of, if you are facing any kind of problem, you are having any kind of doubt, without any hesitation, you have to tell me. Okay. Because it is the fundamental basic thing of electric drives, and you have to understand it properly. So, this one is the x-axis. This one is the y-axis. Okay. So in x-axis, which parameter we have to consider? That is torque. And in y-axis, we are considering omega. Omega. Now, considering, first I draw the thing, then I will elaborately discuss. Okay. So this one this is our counterweight. Counterweight. Okay, and this one is empty cage. And this one is the loaded cage. Okay, so the green thing, okay, the green circles are represent a drum. Suppose the drum is connected over the shaft of a motor, and a rope is connected in that particular drum. Okay, now we know that in case of whenever we are considering the four quadrant means in x-axis we are considering the parameter torque, the output parameter torque, and in y-axis we are considering the omega m, speed of the machine. Now in the first quadrant, the value of the torque and omega is all positive. In the second quadrant, torque is negative, omega is positive. In the third quadrant, both are negative. And in the fourth quadrant, torque is positive, but omega is negative. Fine. Now the green circle is represented by the drum. The drum, that particular drum is connected to the shaft of the motor, and one rope is connected over, or it's placed in that particular drum. Now, one end of the rope is connected with a counterweight. Okay, and another part of the rope is connected with a cage. Now, when the motor is rotating, the drum is also rotating, and the cage is also moving. The purpose of the cage is to deliver load when it is loaded from one edge to another edge, or it is transfer the load from particular stage, one stage to another stage. We have to remember one thing: the weight of the counterweight is greater than the weight of the loaded cage. Okay, again I am repeating, the counterweight, the weight of the counterweight is greater than the value of the loaded cage. Okay, sorry, the value of the loaded counterweight, the weight of the counterweight is greater than the value of the empty cage. But when the cage is loaded, the weight of the loaded cage is greater than the weight of the counterweight. Okay, that is our consideration. That means the weight of the counterweight is greater than the value of the empty cage, weight of the empty cage. But when it is loaded, the loaded cage weight is greater than our counterweight. Now, in the first quadrant, as omega m is positive and we are considering the anti-clockwise direction of the speed is positive. So it is the direction of the omega m is in this way. This is the direction of omega m. Omega m. Okay, the angular speed. Now, as we know that the value of the loaded cage, the weight of the loaded cage is higher than the weight of the counterweight. So obviously, when the cage is loaded, that means the load torque will operate to that particular load. When the cage is loaded, the weight of the loaded cage is greater than the weight of the counterweight, right? So that means in that particular state, in that particular case, the direction of the load torque should be this way. So this is the direction of the load torque. TL. Okay. Now, as we know that as per Newton's law, the direction of the load torque and the motor torque both are opposite with each other. So if the load torque is operating in this direction, so obviously the direction of the motor torque should be opposite. So this is the direction of the motor torque. Okay. That means omega is operating in upward direction. This is the motion. Drum is rotating in anti-clockwise direction, and we are considering anti-clockwise direction of the speed of is positive. Similarly, when the cage is empty, that time the weight of the counterweight is higher than the weight of the empty cage. Now, in the second quadrant also, the motion of the speed is in anti-clockwise direction, because we know that in the second quadrant the speed is positive. So this is the direction of the speed, omega m. Now, as weight of the counterweight is higher than the weight of the empty cage, so obviously load torque, the direction of the load torque should be towards the counterweight. So that is the direction of the load torque, TL. Now, as per Newton's third law, the direction of the motor torque is opposite to the load torque. So that is the direction of the motor torque. So that means the motion is in that particular direction, right? Now in the third quadrant, in the third quadrant, the speed is negative. That means the drum is rotating in clockwise direction. So that means this is the direction of omega m. Now again we know that in third quadrant the weight of the counterweight, the cage is empty, and we know that the counterweight weight, the weight of the counterweight is higher than the weight of the empty cage. So obviously the direction of the load torque is towards the counterweight. So that is the direction of the load torque. Similarly, the empty cage obviously the empty cage, the motor torque will operate towards the empty cage, because we know that as per the Newton's third law, the direction of the load torque and motor torque are opposite with each other. So the motor torque will operate in this way. Okay. Similarly, in the fourth quadrant, we know that here the speed is negative, right? So that means the drum is rotating in clockwise direction. So this is the direction of the speed, omega m. Now the cage is loaded. So we know that the weight of the loaded cage is higher than the weight of the counterweight. So obviously the direction of the load torque should be towards the loaded cage. And as per Newton's third law, again I am telling you that the direction of the load torque and the motor torque are opposite with each other. So this is the direction of the motor torque. So that means in this third quadrant also, the direction of the motion is in this way. In fourth quadrant also, the direction of the motor motion is towards the downward motion. Okay. Now, if we consider the first quadrant operation, then the output power is nothing but omega into torque. That means omega m, the angular speed, into the motor torque. Now in the first quadrant, we can see that the direction of the omega m is positive. That is in anti-clockwise direction. And motor torque is also anti-clockwise direction it is operating. So it is also positive. So P, we can say that the output power, P output, should be is equals to positive T into positive omega m. Positive means positive sign. Okay. Both are positive. So the output power is also positive. But in the second case, we can see that in the second quadrant, the output power that should be is equals to omega is positive because it is operating in anti-clockwise direction, but you can see that motor torque is in clockwise direction. So that means we are getting negative motor torque. So that means minus T into positive omega m. So obviously the output power is negative. Okay. So in the second quadrant, we can say that we can get negative power. Okay. So in the third quadrant, we can see that output power omega is also clockwise. Omega m is in clockwise direction, that is negative. Torque is also in the same direction of omega m, so that is also negative. So minus of omega m into minus of motor torque. So that means the output is plus positive. Okay. Now in the fourth quadrant, we can see that omega m is negative, but torque is positive. Okay. So the P output should be is equals to minus omega m into plus torque. So that means negative. Okay. So this is the fourth quadrant operation. The first quadrant is called forward motoring condition or forward motoring zone. It is called forward, as the output power is positive, so it is called forward motoring. Forward motoring. It is called, the second quadrant is called forward braking. Forward motoring zone, forward braking zone. The third quadrant is called reverse motoring. Okay. And the fourth quadrant is called reverse braking. Okay. So this is the fourth quadrant operation. In the first quadrant is called forward motoring zone. Second quadrant is called forward braking zone. Third quadrant is called reverse motoring zone. And the fourth quadrant is called reverse braking zone. Okay. Where we are getting reverse power, negative power in the output terminal of the motor. That is called braking. And during that time, that thing is represented by, in the fourth quadrant, reverse braking, and in the second quadrant, we told that is forward braking. Okay. Now you have to remember then that a drum is connected with the shaft of the motor, and the motor is rotating in anti-clockwise direction. So the drum is also rotating in anti-clockwise direction itself, and a rope is placed in the drum. The one side of the rope is connected with a counterweight, and another side of the rope is connected with a cage. The purpose of the cage is to shift the load from one step to another step. And you have to remember one thing: the weight of the counterweight is greater than the weight of the empty cage. And when the cage is loaded, the weight of the loaded cage is greater than the weight of the counterweight. So when in the first quadrant, when the motor is moving in anti-clockwise direction, so that means the drum is moving in anti-clockwise direction. That means that time, obviously the load torque will occur when where the load is where the weight is higher. So in the first quadrant, we can see that the direction of the omega m is anti-clockwise direction. Okay, but the cage is loaded, so obviously load torque will occur towards the loaded cage. So this is the direction of the load torque, whereas the motor torque and the load torque obviously opposite with each other as per Newton's third law. So we know that the direction of the motor torque is opposite to the load torque. Okay. Now in the second quadrant, when the cage is empty, that time also our drum is rotating in anti-clockwise direction. So this is the direction of the omega m, anti-clockwise direction. So as we know that the weight of the counterweight is greater than the weight of the empty cage. So now the load torque will occur, or the direction of the load torque is towards the counterweight. So this is the direction of the load torque. Now, if the direction of the load torque is anti-clockwise direction, obviously we know that motor torque will the direction of the motor torque is opposite with the load torque, so it will occur towards the empty cage. That means it is in clockwise direction. Similarly, in case of third quadrant, when the drum is rotating in clockwise direction, so that means the drum is rotating in clockwise direction. So this is the direction of the omega m, the clockwise direction, and we know that time the empty. When the cage is empty, the weight of the counterweight is greater than our empty cage. So obviously load torque will occur. The direction of the load torque is towards the counterweight. So this is the direction of the load torque. Now, as the cage is empty, we know that the direction of the motor torque is opposite to the load torque. So this is the direction of the motor torque. Capital T is represented by the motor torque. Similarly, in the fourth quadrant, when the drum is rotating in clockwise direction, so this is the direction of the omega m. Now the cage is loaded, and we know that the weight of the loaded cage is greater than the weight of the counterweight. So obviously the load torque will occur towards the loaded cage. So this is the direction of the load torque, and as per Newton's third law, motor torque is the opposite direction. It will occur opposite direction of the load torque. So this is the direction of the load torque, that is towards the counterweight. Now the first quadrant, in the first quadrant we are getting, if we consider the output power of the motor, we can see that the torque and the omega m both are in anti-clockwise direction. So we can say the torque is positive, omega m is also positive. So it is called forward motoring zone. In the second quadrant, where we can see that omega m is positive, but as per the direction of the motor torque, it is occurring in the opposite direction, that means the clockwise direction. So as per the direction of the motor torque, that is negative. So we are getting negative output power from the motor. So we can say that this is forward braking zone. Forward braking zone, that means where the torque is negative. Okay. Now in the third quadrant operation, where we can see that the direction of the omega m is also negative and direction of the torque is also negative. So both are occurring in clockwise direction. So omega m is negative, torque is also negative, but so that multiplication of the output power, that is positive. That is called reverse motoring zone. That means the speed is also reverse, torque is also reverse, but the net power is positive. That is called reverse motoring zone. And the fourth quadrant, where we can see that omega m is negative, but as per the direction of the torque, that is positive. So we can say that it is reverse braking zone. So because we are getting reverse power or negative power at the output terminal of the motor, so we can say that that is the reverse braking zone. So this is our fourth quadrant operation, and we have to understand this fourth quadrant operation properly. So have you understood? Arpan, Hira, Poonam, Sanjay, Sumit, everyone.
Yes, ma'am.
Okay, then please. Yes, ma'am. Sanjay, yes, ma'am. Okay, so please draw the entire diagram and draw the direction of the motor torque, load torque, omega m, etc. And write down the symbols. That is the weight of the counterweight, empty cage, loaded cage. Okay. Please draw the diagram. Please draw the diagram, write down the symbols, write down the output power, and write down the specific name of each and every zone. And again, I am telling you, please download the GK Dubey PDF version from Google Play Store, Google Books, or you can get GK Dubey from your senior also. This one is the mother book. If you have power electronics book, you can search in the last pages of power electronics book. Some of the drives topics are there. But as per your syllabus, GK Dubey is the perfect book for BTech level, as well as for MTech level also. Draw the entire diagram. Again, I am repeating. Okay, Hira, completed. Thank you for joining the class. See you in the next class. Then I will start next topic. Okay. Thank you for joining the class. We have
Thank you, ma'am.
laboratory classes also. So gradually we will start our experiments. Okay. Till then, thank you. I'm end up this session.
Thank you, ma'am.
Thank you. Thank you, ma'am.